Okay, so Laplace Transform Lecture 2. Last time I ended up with this example and I applied Laplace Transform to both sides and I got this equation. And this is an equation in Ly. There's an equation in Ly. So, solving for Ly, that's what I got. 1 over, this comes here, s squared plus 5s plus 6 times s minus 2. And I said, not applying L inverse to this. Will give me the answer. So applying Laplace inverse, and you don't have to know what Laplace inverse is, because as I said, if you have a table, since Laplace transform itself is 1-to-1, so if you have a table, if the Laplace of this is this, then the Laplace inverse of this is this, right? So this is two ways. So let's just look at this one. Laplace of E2t is 1 over s minus 2, and this tells me that Laplace inverse of 1 over s minus 2 is E2t, right? So, since this one is 1-to-1, we don't have to find L inverse. Or even we don't have to know the formula for L inverse. Okay, so let's find that. So let me erase everything and try to find that. L inverse of this guy. So use partial fractions. So use partial fractions to find components of this thing. So how do you use partial fractions? First of all, this is s plus 2, s plus 3, s minus 2. So that is this one. Now if this one is irreducible, then I just leave it like that. So this one, it is a over s plus 2 plus b over s plus 3 plus c over s minus 2. And remember, this is in fact an identity, which means the left side should be the same as the right side. So, but the denominator, the common denominator is definitely the same. So I don't have to do anything. So I have, so let's get rid of this denominator. So I have a times this, so that's s plus 3, s minus 2. Then plus b times this, s plus 2, s minus 2, plus c times this, s plus 2, s plus 2. And remember, we can use this trick. I can set s to be anything, because this means identity means it should be true for any s. And please don't tell me that those s's will make the denominator 0. There's some theory behind it. So let's do it, because it gives me the answer. So if I set s to be 2, say, s2, that gives me 1 is 2 plus 3, that's 5a here. No, that is 0. This is 0. This is 0. Only c remains. So I have 2 plus 2 is 4 times 5 at 20. Yes, that's what 20 times c is, so that's 5 is 5. So C is 1 over 2. Then let S be, say, minus 2. Then minus 2 will make this 1, and this minus 2 is minus 4. So 1, and those two are 0. 1 equals minus 4A. So A is minus 1 over 4. And S equals minus 3. And that should give me this one because this is 0, this is 0. And I will get 1 equals, and minus 3 will give me minus 1 here and minus 5 here. So I have 5B. So B is 1 over 5. Well, you can use Wolfram alpha, or if you have Mathematica at home or something else, you can just use that and find these easily. So you just say partial fraction or just something like that on Wolfram alpha, or just do it by hand because although I will give you exams online, so you can do that. So anyway, I have these 3, so let me write it here, and then erase this down here, and don't simplify, so just write minus 1/4 here, and the denominator of this one is S plus 2, plus, and write plus between them, so B is 1 over 5, and S plus 3, and C is 1 over 20, S minus 2. So, I have this thing. So, Laplace transform, inverse of minus 1 over 4, S plus 2, plus 1 over 5, S plus 3. Remember, Laplace, the inverse transform is also linear, so it can be applied to each one of them separately. So this is minus 1/4 L inverse of this 1 over S plus 2 plus 1/5 L inverse of 1 over S plus 3 and plus 1 over 20 L inverse of 1 over S minus 2. Okay. So I know that L, well, I wrote it first, L Laplace of e to power at was 1 over S minus a, right? So the first one is minus 1/4 L inverse of this. A here is minus 2, so it is e to power minus 2t. This one is 1/5 e to power minus 3t. And the last one is plus 1 over 20 e to power 2t. Okay? That's it. So the answer is simply this. This is your yt. And if you look carefully, in fact, the initial conditions, the y0 and y prime 0, have been applied here. Those two are applied. Remember that Laplace transform has those two in it, but since they were 0, they didn't come into the picture. And most often when we're dealing with forced vibrations or forced something, and that force is the right-hand side, you usually start from 0. You usually start from 0. So, and there are ways to make that initial condition to be 0. So, most problems here are like that. That is why 0 is 0, y prime 0 is 0, or the initial conditions, even if you are more than second order, those are all 0, most often. So that's it. That's the what Laplace transform can do. First, you apply Laplace transform to both sides and change that into a function like this, which is usually some kind of rational function, or in the numerator you might have like e to the power something. So you can just put it away. You will see how to deal with those numerators, but you might have some constants over that. But anyway, you have to look at the table and try to come up with something which looks like functions in that table, or the Laplace transform of some functions in that table. So let me give you another example. So let's see. Example. Remember, if try to solve that using the method of indeterminate coefficients, undetermined coefficients. You will see if you try to solve that, you will get something like the c1 e to the power minus 2t plus c2 e to the power minus 3t plus what was it, 1 over 20, something like that, 1 over 40. I guess it was 1 over 20. E to the power 2t, something like that. But then you have to apply the initial conditions to find C1 and C2, right? And you already have to find this 1 over 40 or 1 over 20. So that's a lot of work. For this, if you just don't panic and do the partial fraction, which you can do it online, so don't worry about that, then this is in fact an amazingly nice way of solving certain differential equations for which you have Laplace transform of the right-hand side, the forcing function. So let's go with y double prime plus, well, let's go with the same one again, because we know that the answer 6y. Let's do this. Minus, and plus 6 will be minus 6, right? And let's make it a little harder. So 2t again plus cosine, say 3t. So let's apply L minus y prime minus this y, and that's a plus 2t plus cosine 3t. So this side I know is s squared minus s minus 6, right? L of y. Well, I didn't make any assumptions on them, so let's say y0 and y prime 0 and all 0. So when I make the assumption, I am not worried about those other constants here. So, and on this side, L of a, well, I have it over the right, 1 over s minus 2, and cosine, I can't, I'm not that, I don't have it in my mind, so let's see. Cosine will be s over s squared plus a squared. S over s squared plus omega squared, which is 9. Okay, so I have Ly is I can solve them one by one. Remember, I can do one by one. So let's do this one first. So let's this one, so it will be this one, say, and then this one. So let's get rid of this. First solve this. So that is what's that? So I have s squared minus s minus 6, s minus 2. Okay, So I will solve this too. S squared minus s minus 6 ly was s over s plus 9. So I will solve these two and then put them together. So y is L inverse of this 1 over, well, s minus s squared minus s minus 6 is 2 times 3 is 6, so that is s minus 3 s plus 2, s minus 2, right? S minus 3, let me check, minus, that's minus s, and minus 6, yeah, correct. So I have this thing, and so I have to do the partial fraction, 1 over, let me write it, s plus 2, s minus 3, a, s minus 3, b, s plus 2, c, s minus 2. So I have 1, same as a times this times this. Plus b times s minus 3, s minus 2, plus c, s minus 3, s plus 2. Right? So if I put s2, well, let's just make these two 0. 3 and 3 makes those two 0, so if I put 3 here, 3 plus 2 is 5, minus 2 is minus 1, no, it's 1. So 1 times 5, a will be 1/5, right? So 5, 1, 1/5. Let's write it here. B, if I set s negative 2, will make this 0 and this 0. Negative 2 will give me negative 5, negative 4. That's 4 times 5, 20. So b is 1 over 20. Minus and minus, minus, that's plus. And last, if I set s to be 2, this is 0, so this 2 will give me minus 1 plus 4. So that's minus 4, so c will be minus 1 over 4. Okay? Minus 1 over 4. So I have to find here. So for this one, let me erase this. And it's like the previous one, so I'm not going to elaborate more. So part of the solution will be the solution of this, and that will be so that will be 1/5 the Laplace inverse of this e to power 3t. The other one, 1 over 20 e to power minus 2t, and the last one is minus 1/4 e to power 2t. Okay, so that is solution to this one. So let me write here. Part of the solution is so yt will be 1/5 e3t 1 over 20 minus 2t minus 1 over 4. So let's plus something. So let's find the other one. Okay. So let's erase this and this. Now we have to solve that. So what do we get in the end? I have Ly is S times divided by this thing, which I found this to be minus 3, that's plus 2, right? Times, that was S squared, not S, times S squared plus 9. Okay. Oh, okay. Well, I'm not going to use any system. Let's do it by hand for now. So this one will be A over over s minus 3 plus b over s plus 2 plus c s plus d over s squared plus 9. Okay, so if you have square, a quadratic in the denominator, which is not, cannot factorize it, so it's irreducible. This is irreducible, you cannot factorize. Then the numerator for partial fraction will be a linear function of s, cs plus b. Okay, now let's get rid of the denominators. And so I have to solve this. S is equivalent to a times s plus 2 times s squared plus 9 plus b times s minus 3 times s squared plus 9 plus cs plus d times s minus 3 s plus 2. Okay? Well, I can use that method to find at least, well, let's see, if I set s to be 3 or minus 2, this will be 0. So I can find these two. So let's do it. So let's say s is 3, and this gives me 3 plus 2 is 5, and 3 squared is 9, and plus 9 is 18. 5 times 18 is 90. So I have 90. A equals 1. So A will be equals 3, in fact. So no, let me write this. So when S is 3, I have 3 on this side equals 90 A. So A is 3 over 90, or 1 over 10. Okay. Then S is 2, again minus 2, sorry, and that gives you minus 2 equals, this will be 0, so that is minus 2, minus 3 is minus 5, that's 4 plus 9, 4 plus 9 is 13, so minus 5 times 13 is 65, right? 65, and that's minus 65 B. So B is 2 over 65. 2 over 65. So let me write them on top. And so I have 1 over 30. And B is 2 over 65. And now, to find CS plus D, well, I can use any number for S. But if I put S0, let's see what happens if I set S0. As I said, you can use online to do this, but so if I set S0, I will get 0 equals, S0 will give me 2 times 9 is 18 times A, which is 1 over 30, plus 0 will give me minus 3 times 9 is minus 27 times B, which is 2 over 65. And here I will get plus B times 0 is minus 3 plus 2 is minus 6. Oh my goodness, okay. So, so that will give me D. I'm not going to waste your time to, let's see. Maybe I can do it quickly. So that's 18 over 30 minus, so it's minus because it should go to the other side, minus this, plus 27, that's 54 over 65 over minus 6, right? So I don't know what that is, you can find it exactly. Now that we know D, we can just use another say S equals say 1 and find S, find C. Well, I guess I need both of them very carefully too. So let me see if I can bring Mathematica on my computer and just do it for you. But what happens is this. So let me. So at least I can come up with 1 over 30 plus 1 over 30 e to the power 3t plus 2 over 65 e to the power minus 2t plus something which is this. So let me do this quickly here. Let's see. One over. Did I find 1 over 90 or 1 over 30? What happened? One over 65 is correct. It gave me 1 over 65. But yeah, it gave me 1 over 90. What happened? I still so that was what A. So that was S is 3. So that's 5. 9. That's 18. 5 times 18 is 90. Why does it have 1 over 90 here? I just don't understand. Oh. Yeah, that's S over that. Sorry, I was going to make a big mistake. So 1 over 30, 2 over 65 is correct. So this will be, let me write it here. So it will be, those two are correct. And then that is minus 5 over 78. 7, 8, yeah, 8. S minus 3 over 78. Okay. So this one are okay. But what would happen to this one? What is the L inverse of this? So let me erase everything and try to find L inverse of that for you. Now, if there is an exam, you have to come up with this, then you have to find the L inverse. And you have to show me how you do it. Don't just write the answer. So L inverse of this is minus 5 over 78s minus 3 over 78 s squared plus 9. Okay, let me look at the table and see if there is anything which has s squared plus 9 in the denominator. So well, maybe I should erase everything. And remember that I have cosine 3t, which I will get cosine and sine 3t. So I don't get that one. I need cosine and sine. Cosine omega t was what was it? Cosine was s over the square plus omega square. And L of sine t is omega. Yes. Okay. So now what is suppose S is S, omega is 3. So for me, omega is 3. So in the numerator here, I have something like this. Some constant times L inverse of new S on top, S squared plus 9, and some constant times L inverse of omega is 3, so I need 3 here, S squared plus 9. Okay. So let's look at this. Okay, so if I have an S here, I need an S here, so the coefficient here is simply minus 5 over 78. Over there I need a 3, I have a 3 over 78. So I have minus 1 over 78, right? Because I have 3 over 78, I need the 3 over there in the numerator, so 1 over 78. So this will be minus 5 over 78, and that is cosine 3t, and this one minus 1 over 78 sine 3t. Just add this to those solutions and you have the solution. Okay, so the complete solution. And don't forget to put them together because they were e to the power minus 2t or minus something. So there were two of them, just add the coefficients and in the end you have the complete solution. Now, if you wanted to do this without Laplace transform, you had to make this. So you have to say, okay, the particular solution has two parts. Y is a e to the power 2t, and the P2 would be b cosine 3t plus c sine 3t. With the initial conditions, well, with the initial conditions were these. And if you solve this, you would find this a, I can't remember what that was, but the b would be this, and the c would be this. So you see this method, at least for me, it makes life much easier, although it might not really give you the physics of the problem. So what's going on? Unless you are studying, say, electrical engineering, and you have developed that, that intuition, understanding of what the frequency domain really means. Or by just looking at this, you can say a lot. Okay, so I said I would give you an example before I start step function and analyzing step function, and because that needs like some time, I can give you an example. Suppose we have this spring mass system. So this is a dash pot and the spring K. And remember the equation, so this is say y, and let me write y double prime. So I have m y double prime plus c y prime plus k y. And let's assume that there is some magnet here, some device that produces some force. So it just pulls this down somehow. So I have a force on this side. So it can be, say, cosine some omega t, say cosine of, say, 3, cosine 3. So it might be just up and down, up, down, up, down. And then this y will be like response, right? Y is response to a system. So this system is some forces applied to the system, and now if I can just write F here. Let me just write Ft. Let me just write Ft, and not because let's say just some function of time. Ft. So Ft. If I add applied Laplace transform L, I will get this. M s squared plus cs plus k times ly is some function of s. L of ft is a function of s. So I have ly is in fact some function of s over ms squared plus cs plus k. So if I look at this as input-output, and let's call this y, in fact, ys, then I have an input, fs, and my system is in fact this. My system is this function. And the output is ys. And the interesting thing is that the ys equals this times this. In the language of, say, systems, say control systems, for example, this is called a transfer function. Transfer function. And you see this transfer function is a property of the system. It has nothing to do with this forcing function. This is m, c, and k. So the transfer function is the property of the system. So if you have a system and you calculate its transfer function, it can be just a gigantic system, and then you apply different forces to the system, different fs. Like here, you can apply a sine, a cosine, a to the power something, or a combination of them. And that, if you write it down in the Laplace transform form, in the fs form, then ys is simply this times this, and as you can see, ys is this times this. So this is like fs times the transfer function. Okay, so it's that easy. It is that easy. It is simply fs times the transfer function. Now, change fs. If you have a differential equation solver, you can immediately solve it. And also, as I said, you will get some intuition here. When you look at this transfer function, you can say a lot. You can immediately, if you have numbers here, you can immediately say, for example, if this system is, say, stable or not, by looking at the C, for example. If the C is positive, then it might be, right? If this K is negative, well, C plus negative, that's something else. But if K is negative, then definitely it's not stable, because you will get positive under the radical, so the solutions will be e to the power something. Well, it might be. It depends on e to the power. If it's e to the power negative, then it just dies down. But anyway, by looking at this transfer function, you can say a lot. And in control theory, each system has its own transfer function. So you can combine the transfer functions, or you can even have some feedback, and the feedback comes into the system, and there are rules to add those transfer functions when there's a feedback. Putting all that together, you will get the transfer function for a system. That might be like a gigantic, say, I don't know, a ship or an airplane, something. That's one way to analyze systems like that, like big systems, finding transfer functions, and then when you apply force or forces, it might be, it might have different inputs. So I told you at the beginning that this, I will give you an example. Well, this might not be a good example, because you don't really see what's going on, what's the input, what's the output. But maybe this makes a lot of sense, that there's like a magnet here, and this, if this is like iron or something, steel, for example, then if this magnet can, if this the intensity just pulls this up and down, if you change this magnet, the intensity, so it might go up and down. It might just pull it down and let it go, something like that. But anyway, so different forces, and using the transfer function you can solve the problem. So you can just find Laplace inverse of this guy here, and you have yt. That's it. So this multiplied by this Laplace inverse, you have yt. Okay. So that is for students who at some point should take a course in control systems, and if you open a control system book, perhaps the first chapter is Laplace Transform or solving differential equations. Okay, let me start another function. Let me see. Which section is that? The step function. So that is like 6.3 in my book. That is step functions. The book uses a terminology called YUCT. So the function is a UCT, and it looks like this. So this is point C, and it is like this. This is not included, and it's 1 here. It is included. Okay. So UCT, in fact, is this function. Is 0 for t less than c, and is 1 for t bigger than or equal to c. Okay? Now, what is Laplace transform of this? Now, this function we will see perhaps next time how it is used in modeling so many inputs. Input that you might see in different machinery, like in electrical engineering, for example, in control engineering, whatever, and that is like a pulse. Suddenly something starts, like you turn on a light, suddenly something goes up. It's like the voltage goes to some peak, say. Switches, for example. So they have to be analyzed. They have to analyze very carefully because those kind of inputs are applied to a system which has a transfer function which comes from maybe a second order differential equation. So let's find Laplace transform of this. L of UCT. Remember, Laplace transform was 0 to infinity of e to power minus st UCT dt. Well, this function is 0 up to point C. So it's 0 times this, and integral of that is 0. But it starts at C. So it is from C to infinity, e to power minus st times 1 dt. Okay, so that is in fact minus 1 over s e to power minus st from C to infinity. So that's minus 1 over s e to power minus infinity is 0 minus e to power ct. Right? So this guy here, it's Laplace transform, is minus minus is plus e to power minus ct over this. Right? So that is the step function. So if you see e to power minus s, let me double check here. Yeah. And s is definitely bigger than 0. So, well, that should be. Okay. So this, it's like if I had something like this. So let me, how much time? Yeah, I have some time to at least write down the formula. So if I have a function like this. So let's say I have an equation. So example, I will start and then maybe finish next time. You say 5. You 8. Okay. So L, apply L. Then on this side again we have done it several times 5s plus 6 L of y. Now this side, what do I have? That's e to the power minus 8t over s. So L y will be this thing, e to the power minus 8t over s times s squared plus 5s plus 6. So I have to find Laplace inverse of this. L inverse of this guy here. Let's write e to the power minus 8t here times 1 over s times s squared plus 2 s squared plus 3. Okay. So this is a very special. This is a special case. I can find Laplace inverse of this. But what happened here? What is e to the power minus 8t? What does it do to that? Because I might have e to the power minus 8t on top of something like this, right? Or on top of something like this. Well, this one is okay because that's another step function. But what is the other one? What is e to the power minus 8t over this? What is the Laplace inverse of that? 8. Sorry, that is 8s, right? 8s, not 14. Yes, that was yes, right? So, what is it? What is the inverse of that? Laplace inverse of something like this. Well, I might eventually have to find something like this. What kind of function gives me this as Laplace transform? So I have to investigate some functions, and you might guess that it should have to do with the step function. Maybe it's like step function times like some sine or cosine, right? So you might think that it should be step function times sine and cosine. So what is step function times sine x? Just some. Well, let's erase this and look at the picture. Say, so what is u8 t times say? I have to do here. No, that's not 2. That's 1. All right. So let's say this thing. Well, let's say I have this. Let's say I have s squared plus 9. No, I guess this was not squared. Sorry. What am I saying? I'm just getting tired. ut cosine 3t. See. What is the Laplace of this thing? And first of all, what does this look like? So this cosine 3t, well, if I start at 0, then this is something like this, right? And what are these points say? That's cosine 3t equal to 0, so that is pi over 2, that's pi over 6, for example, one of them. And pi over 6, for example, and something. So what does this do? What does this u8t do to a function? Not just cosine. So let me just say I have a function ft that looks like this. Then u8t ft is like this. And 0. So from 0 minus infinity to 0.8, that is 0, and then suddenly it is the same as this function. So you can guess what happens. So it's like the integral instead of going from 0 to infinity, will be from 8 to infinity, right? So that will be from 8 to infinity, because everything is 0. So this will be the integral from 8 to infinity e to power minus st cosine 3t dt. Right? So, well, it's not that hard to find it, although you have to find it, say, using integration by parts several times, but it's not that hard. So next time I will discuss this general form and tell you what happens if you have u8t and how you can find it easily, or how you can use, for example, the Laplace transform of this one to find. And you can guess what happens because you can take this to 0, right? So that's t from 8 to infinity. So t plus t minus 8 goes t plus 8 t minus goes from 0 to infinity. So I will discuss that, and by changing some variable, you will see that it becomes very easy. Okay, so let me stop here and continue this next time. And sorry, I was so tired. I was teaching another class before this. Okay, see you next time.